This section of the waste management lectures correspond to solid waste characterization. For prevention and minimization, we need to identify the properties of a solid waste, and we need to identify the sustainable options for waste management. Depending on the type of waste, the amount of waste that is being generated, and the weather conditions, we will have different constraints and different types of management. In Las Vegas, in USA, we have the landfill, one of the most modern landfills all over the world. This landfill receives 10,500 tons per day. It receives municipal solid waste, and the main characteristic of this landfill is that methane is being captured. So they actually produce energy from this methane, from this biogas, and the waste is being well managed in order to avoid environmental and health problems. But then what about other regions where probably space is a constraint? This is an example of a city where actually the main problem may be limits on space, for instance. So this is Shanghai, China, and this is a landfill that is outside of Shanghai. It receives from 6,000 to 10,000 tons per day, and the main health implications are methane emissions. As you can see on the picture, you can see that it doesn't look like well organized as the previous one, but it has to do with it has other weather, and it may have other characteristics, the waste that is being generated. So thinking about how characteristics and distribution heterogeneity of the waste, we're going to look now at the Northern Territories in Australia. So in this case, space might not be a constraint, but the collection of the waste among communities is the main constraint. Also, for instance, one of the main issues in Northern Territories is the fact that hazardous or recyclable wastes often end up as landfill. So imagine the environmental problems that this can generate if this material is being disposed along with other type of waste. What I'm trying for you to start thinking is that the waste hierarchy may be also subject to the characteristics of the waste. So we're going to start now with solid waste characterization. What are the main characteristics that we want to know on waste? So we have physical and mechanical properties, chemical properties, and combustion properties. And each of these characteristics imply how much volume of waste we will have and what are the alternatives for the management. So we're going to talk a lot in these lectures about waste generation per capita, and this is fundamental for the waste planning, so for collection and treatment operations. We're going to talk about physical composition, waste density, and waste density, for instance, is relevant for waste operation equipment, vehicles, and waste containers, and as well as other type of equipment. We're going to talk a lot about moisture content. Think about why it's important. It can influence waste degradation and stabilization, as well as energy recovery from waste. Imagine if we have a combustible material that can be sent to incineration, but it has a high moisture content. It might affect the efficiency of the system, for instance. Or, on the other hand, if we want to treat this waste through, if it's an organic waste and it has a very low moisture content and we want to treat it for biogas production, think about how this will affect the process. We're going to discuss also particle size and size distribution. And this is a characteristic that allows to assess and characterize waste concerning materials concentration in a specific size, and it has also implications on the equipment, the type of equipment that we will need. Chemical properties are very important when we're talking about organic waste. But also, I mean, for instance, the pH is very important because it also tells us the level or the stage where the degradation, organic degradation is happening. But also, it can affect the equipment due to corrosion, and also it can enhance leaching of metals. The chemical composition helps to define best waste treatment to be applied. It also indicates the presence of harmful substances, which also influence the adequate waste treatment. For instance, for composting, we want to know the relationship between carbon, nitrogen, phosphorus to know whether it's adequate to do composting on for the type of waste or not. We want to know other components within the waste, for instance, toxic chemicals or compounds that can inhibit the bacteria that can do degradation processes, whether this degradation is for composting or for biogas production. We're going to look at the low or net calorific value of the waste and biological features. This can help us to define the type of treatment. This is an example on the waste properties of different materials, and we're talking here on the left side on moisture content and density. So the typical density of the waste and the moisture content. As you can see, food and jar waste are the ones that contain a higher percentage of moisture content, while other materials contain less amount of moisture. Then on the right side, I'm showing you the energy content, and this is the net calorific value. Why do we care about this information? Well, because we want to know whether this material can be incinerated, and if it will provide energy, or it will require to have additional fuel to incinerate the material. This is the chemical composition of different types of waste. The most common ones are municipal solid waste, which are food waste, paper, cardboard, plastics, textiles. And this is the disposed waste composition, decay rate, waste moisture content, and chemical composition of individual waste components. Why do we need to know decay rate? Decay rate means the velocity of degradation, biological degradation of the material. So we can see that food waste has a very rapid degradation rate or decay rate, while for other type of material the degradation is very slow. For instance, wood. As we have discussed before, we have the moisture content, and then we have carbon, hydrogen, oxygen, nitrogen, sulfur, and ash. If we have the percentage of these elements, we are able to know the potential amount of methane that can be produced, or the potential amount of air that is necessary for incineration of the material. So to better understand these concepts, we are going to do our first exercise, and this exercise is about calculating solid waste generation rates. We're going to use the following data to calculate the composition of the generated waste for the outlying conditions. We have the component and the disposed waste composition. So this is the amount of waste that was directly disposed, not the amount of waste that was generated. Okay, so we don't know the amount of waste that is being generated, but this is what was sent to landfill. Let's put it in that way. And then the information that we have is that the amount of food was reduced because grinders were in some of the homes. In 20% of the homes, we had food grinders, which are the ones that are commonly used in the United States for grinding the food in the sink. And then We also have information on recycling. We know that 11% of the generated municipal solid waste was recycled or is recycled. And we also know the composition of the recycled municipal solid waste. Okay, to start with this example, we need to have a base, a calculation base, and we are going to use kilograms. So everything will be based on 100 kilograms, and now we can convert the percentage to kilograms of disposed waste. So that means that we will have the same numbers, but now this will be in kilograms. This is a mass balance, a typical mass balance, and the mass balance will be generation will be equal to what was disposed and what was recycled and what was diverted. So we know what the value that we have now is disposal, and we have information on recycle, and diverted will be the grinding, the what was grinded from the food waste. All right. So the total mass balance will be equal to so the total generated, which we don't know the value, will be equal to what was disposed, which was 100, plus what was recycled, and for that we know that 11% point, or the fraction of 0.11 was recycled of the total amount generated, plus what was diverted. So at this moment we cannot solve x for x, but we can actually find how much was diverted. So the only thing that was diverted from this exercise was food waste. So now we can go to a balance on food waste, and that will be equal to what was disposed. So we can have disposal equals to what was generated minus what was recycled minus what was diverted. So disposal of food, this is corresponding to food, and this is 9 kilograms equals to what was generated for food minus 0 because nothing was recycled here. Actually, the food was not recycled according to the information that we have. And we know that 20% was diverted, right? Or was grinded from the total amount of waste, of generated food waste. So in this case, now we can actually solve this equation for the total generated of food, and this will give us this result. So this is the total amount of food waste generated. So now we know how much what was diverted of the total amount. And the total amount of what was diverted was 9 kilograms minus, oh, sorry, well, it was 9.4736 minus 9 that was disposed, right? So this is equals to 0.4736. Now we can finally solve for x, which is the total amount of waste that was generated. And if you do the calculation, you should have a value of 112.89 kilograms. So this is the original amount of waste that was generated, but what was disposed was 100 kilograms, right? So from here, now we can calculate the total amount of waste that was recycled. And this corresponds to 12.418. Sorry, I'm not following any order on the decimals. We should stick to one number, a certain number of decimals, kilograms. So if we're going to be strict, I can add here one additional decimal. So this is the total amount of what was recycled, and with this number we can actually now calculate the amount of recycled according to the percentages, the information on the percentages that we have here. So we have a percentage for paper, glass, for all these materials. From the total amount of what was recycled, you have the values, all right? So going back to our slides, now we can see the final result. So if you make these calculations, these are the values that you should be able to get.